I think all the work I have been doing or have done, I think I like it very much. But I was very much excited when I managed to do an experiment here in Pakistan with the helium atom. Once lithium-6 is excited, then you can use another laser to ionize it. Now, once it ionizes, now you can apply a magnetic field. Or you can separate lithium-6 and lithium-7. So I have no regrets coming back from Germany and establishing a laboratory in Pakistan and contributing positively. I think no regrets. The government has really honored me a lot. Maybe in the internationally they are saying 40 to 60%. 60% applied and 40% basic science. But I think 50-50 is fine. There's no hard and fast rule.
But
We should support both basic as well as applied sciences.
Assalamu alaikum. Hello, everyone. My name is Al Mustafa, and this is COMSTECH podcast. Today, our guest is a prominent scientific figure, Professor Dr. Muhammad Aslam Baig, Secretary General of Pakistan Academy of Sciences, and distinguished professor of atomic physics. Thank you very much, Professor.
It's a pleasure to be here. Thank you very much.
Professor, let's start with some quick question. Who is your favorite physicist?
Well, I think is no question about that. My favorite physicist, Abdul Salam. He is the only Pakistani Muslim Nobel laureate. He got his Nobel Prize way back in 1979. And that is the year when I got my PhD from Embark, London. So he was there. So I have this honor to be at Imperial College when I got PhD and he got the Nobel Prize. I think he is a remarkable personality, excellent behavior, and he is very much devoted to Pakistan. And he has done extremely useful work for Pakistan to establish different institutions like Pakistan Atomic Energy Commission, NIPG, and then SPARCO, Pakistan Science Foundation. You name any institution, I think it was initiated by Professor Abdul Salam. And in those days, we were lucky to have another very towering personality. He was Ishrat Usmani. He was a man who actually started the Pakistan Atomic Energy Commission, and Salam was advisor to that. And the success of any institution depends on the man behind the institution. And he was an excellent leader. He selected excellent persons who developed this facility, and ultimately we became the nuclear power. I think it's only due to these very prominent personalities. In addition to that, there are other people who were so devoted to our program to develop science and technology in Pakistan. I will name a few of them. One of them is Professor Ishfaq Ahmed Saab, who was the chairman Pakistan Atomic Energy Commission. And then Dr. Abdul Qadir Khan, he joined later. So he was made the head of KRL, where uranium was enriched. And I think there are so many other people who have really devoted their life. And ultimately, we became a secure nation. But in all these things, there is another person who really devoted his life for Pakistani science. His name is Dr. Rafi Muhammad Chaudhry. He came to Pakistan way back in 1953 after getting his PhD. With Rutherford, the only person who worked there. And interestingly, and there is a picture with 25 people. And all 24 people, they got Nobel Prize. It is with Rutherford, except Rafi Muhammad Chaudhry. I think he just missed this opportunity. But he devoted his life to Pakistan, and he established a very excellent facility known as a high tension laboratory. And all the people who have worked in our nuclear program, they have 90% of them trained in that laboratory. So I think these are the few people I will always remember them, and I respect them a lot because they are the towering personalities and who have developed, helped to develop Pakistan or place Pakistan in this position where we are now. Thank you.
Okay. As you mentioned, Imperial College London, how did your PhD at Imperial College London shape your scientific methodology?
I think it's a long story, but I would like to cut it short and tell you, I belong to a very poor family. My parents, they migrated from India, and I was born in 1950. And we were living in a village. There was hardly any facility of school education, but my father, he helped me. Then I was sent to another school about 50 kilometers away for my matriculation. It was in Rahim Yarkhan. And from there I was sent to another very good college. It was Montgomery in those days, government college. Nowadays it's called Sahiwal. I did my FSc there. And then BSc from Punjab University. And then MSc from Karachi University and MPhil from Karachi University. My father's idea was you should move around, look around, and learn to survive. After every 2 years, new place, you have to have new friends. I think that I learned a lot, culturally as well as scientifically. In 75, I never met Salam, but in 1975, I got an invitation to attend Winter College on Atomic, Molecular and Laser Physics. I applied for it. Luckily, I was selected. So I went to International Center for Theoretical Physics, Trieste. It was established by Abdus Salam. ICTP. And there I met Salam for the first time. So I went there for 3 months, and I really learned a lot. I met different people. Nobel laureates were there. And Salam asked me, what about your PhD program? You want to do PhD? I said, of course, I would love to have. And then he offered a very generous offer. He said, you can apply to different professors and you can write my name as a referee. And reference of Salam, I think that was a remarkable thing. So I applied at 5 or 6 universities, and I got acceptance from every university. I went to Salam Sahab. I said, what should I do? And he said, it's up to you. I said, I want to join Imperial College because there was an offer from a professor there. He said, I think it's a good idea. And that's how I ended up at Imperial College. And I started my PhD there. But before joining PhD, I had already 4 publications, international publications that I managed to get from Karachi University. And my professor was so much impressed. He said, well, you have already got 3-4 publications internationally. You don't need any PhD. You are already a PhD. So he sent me to Germany. He said, go there and establish a laboratory. So I went to Germany and Bonn University, and there was a professor, Wolfgang Paul. He was an experimentalist, and he got the Nobel Prize in 1985. So I worked with him, and our topic was to establish a laboratory of synchrotron radiation, to look for the interaction of atoms with the synchrotron radiation. You know, synchrotron radiation is a human attempt to make an atom. You take an electron, You inject in the electric field, you accelerate it, then magnetic field, you turn it around. And so electron will move in a circle orbit. And when the electron moves in a circle orbit, from tangent point, it emits a radiation. That's a very intense radiation. So we're using that radiation and interact with atoms and molecules to study the internal structure, like photoionization or to study double excitation. And that was my topic for PhD. When I got my PhD, Professor Paul, he offered me a position in Bonn University. So I went and I joined Bonn University. I stayed there till 1986. And then Professor Salam, he asked me, now you should go back to Pakistan and try to establish some facility there. And that's how I came back after spending 10 years in Europe, although I was very established, I was famous there. But it was the order from Professor Salam, and I have to come back and join Quaid-e-Azam University. Here I came, and then I established this atomic and molecular physics laboratory. I worked very hard, and I started from the scratch, and I brought this laboratory up to the international standards. And we were publishing papers. I produced more than 35 PhDs, about 100 MPhils. And all my students, they are working in these R&D organizations like PAC, KRL, NESCOM. You name any organization, you will find my student. And 3 of my students, they are professors in USA. I think that's a great honor that you produce a PhD, he qualifies to become a professor in America. One is now a head of the Department of Physics at Ohio State University. So I think that's a great thing. And one is at, I think he's working at John Hopkins University. So I feel this is how one should contribute towards science and for the development of your country. Teaching, of course, is an excellent idea. You nourish young minds. But at the same time, you should always try to do something for your nation. And I have always this in mind, how can I contribute for my country? Let me tell you one more thing. That once I masterminded the basic sciences in physics, in atomic physics, lasers, then I started doing some applications. The first thing I made was atomic beam apparatus. And with that, we tried to enrich lithium, lithium-6 and lithium-7. And that was a very significant contribution, that how you can enrich isotopes with the lasers. And I demonstrated that. And then I had this one in my mind, how to identify different materials in any sample, like in ores, in stones, or in some anything, alloys. That means if you have an alloy or anything, you want to find out what is the composition of it. You can reconstruct it. And that was in my mind. So I developed a technique known as laser-induced breakdown spectroscopy. This is a very simple technique, but I started in Pakistan way back in 1995. You take a laser beam, high-power laser, and you focus on the surface of any material. As a result, the material will be evaporated, it will ionize, it will form a plasma. So plasma light, you can actually register the light, and that will give you the emission lines of all the elements which are present in the sample. Just like we have a DNA, similarly every atom has its own resonance line or its own structure. So from there you can identify which element is present. And once you have identified, almost you have done more than 80% work. And the next step is how to find the composition quantitatively and qualitatively. First we do qualitative, then quantitatively. And for doing quantitative work, I developed another apparatus. It's known as the time of flight mass spectrometer. This apparatus is banned for Pakistan. The reason is that if you enrich any material, you can judge what is the percentage of your enrichment. So we were not given this apparatus. So I decided to make on my own. So I designed it, I fabricated, and then I demonstrated. And we managed to do a lot of work on the isotopes. Like cadmium has 8 isotopes. And once I made this equipment, we resolved all the isotopes. I think that was a great thing. And then I immediately thought I should file a patent. That is another story, but this apparatus, once I built, I published it. And the publication was such a remarkable journal that they have appreciated a lot. And I got a letter from the editor that your paper has been downloaded so many times. So then you feel so happy that at least you have done some work. So after doing this work, I continued my journey. Then I wanted to do something different in laser physics. I established a laboratory on the fiber lasers. You know, fiber lasers, they are very common nowadays. Normal laser is very heavy and very cumbersome. You have to adjust your lenses, mirrors. Whereas fiber laser has a quality that you can take it anywhere. Its size is very small. So we established this laboratory, and I think now we can produce fiber lasers of any power. Although it's purely academic work, and we are publishing it. Whenever we develop a new laser, we publish it. The next step was to change the continuous wave laser into pulse laser so that you can get high energy. And for that, we developed another technique known as saturated absorber that will control first the power, and then it will release once it's saturated, and you get a burst of power, a beam of laser. And that was a very, very good thing. And we published a paper in Scientific Report about different possibilities, how you can generate short pulses from a fiber laser. Let me tell you one more thing. Yogi has got Nobel Prize this year, and he had worked on saturated absorbers. Particularly, he worked on MOFs. So we are also making MOFs, molybdenum or iron MOFs, and these MOFs we are using as saturated absorber. So I was feeling so happy that at least we are following Yogi and we are trying to do a very similar work. And my students, they are really working very hard. But the thing is, you have to guide them. You have to give them the direction, how to do something useful, not only for yourself, for your country. I think that's very, very important. And then I established another facility. It is known as the pulse laser deposition of thin films. Principle is the same. You take a laser, you evaporate something, on top you put substrate, and then you can deposit any thin film. So this is again a very, very useful thing. So we made the saturated absorber using this technique. And recently I have established another facility to make devices like sensors. We have got this facility also. So I'm really trying to do as much as I can within my capacity.
Great. I want to ask you about laser, but before that, I need a description about or the key differences between scientific ecosystem at Imperial College London and Germany.
Well, there's a big difference. One difference is that the British people, they are very open. they will not bother too much. What they want, they need some output. They will not bother that if you connect any equipment, you need a proper plug or the fuse. I think that is a much relaxed way of working. And then the British people, I think they are not putting so much pressure on you. They want that you should do research in a relaxed mood. Whereas in Germany, they are very precise. Their precision and tolerance, they need perfection. And perfection comes through your dedication and your concentration. You cannot plug any power supply without first checking what is the power rating, whether it has a fuse or has a proper plug or not. And this is a very big difference. As an experimental physicist, I have noticed this thing. Otherwise, I think Germans are very, very careful people. They work very hard and they come early in the morning, and normally they have a tea within their after breakfast or coffee, and they used to go almost 11:30 for lunch, early lunch and mensa, and at 6 o'clock in those days all shops are closed, and they have to rush to the bakeries to collect bread, and that's it. But I think the working in Germany is tough, but you have to do everything very, very precisely. And there is a big brother is always watching you. Whereas Britain, I think they are very relaxed people. But otherwise, there is hardly any difference. Both countries, I think they have their own character, but I think ultimately they are very good. I used to go to my institution early, about 8 o'clock, and I will not return home at least 8 or 9 o'clock in the evening. So at least 12 hours. That is a minimum requirement if you really want to survive in German culture or German scientific community. German professors, they work even more than that, 12 to 14 hours. Whereas in England, I think is 8 hours. If you go to America, you have to add 1 more hours in it. And that depends if you want to survive. But if you want to excel, you have to add a couple of hours more. So I think this is a very tough life. I used to, very frankly, talk to my professors because they are always busy working in laboratories. Whereas our technicians, they will come at early in the morning at 7 o'clock because they have a relaxed timing, and they will leave at 2 o'clock. And then they go and enjoy their family life. Whereas professors, students, they are very tight. I have seen students crying, even professors. They lose their girlfriends because they have no time if they want to survive in science. And the family life of professors is not ideal, I must say, not ideal. They're always fighting because the only option is to have a girlfriend or wife from your discipline. So you both are busy. One thing I noticed, most of the professors, they are much liked but they like their secretaries because they're always there to help them. So I think this thing is, I haven't noticed it. I might be wrong, but I have noticed that the family life of professors is really, they have to make a lot of sacrifices. Whereas in our society, I think we are much relaxed people. We take care of our families. We give a lot of time to families. We hardly work. It's only you go 10 o'clock and at 4 o'clock you go home. I think this is not a good thing. That's why we are lagging. We are much behind as compared to European or American. In Pakistan, when I joined Qaid-e-Azam University, This was my routine, to go to the university at 8 o'clock and come back at least after Maghrib Namaz. I mean, this was my routine. I was living next, very near to my university. My family was living, but I used to take my lunch with my students in the university, so that I can discuss with them. I can talk about their problems, try to find their solutions. And I was using that time very effectively, having lunch with them, 1 hour, 2 hours, we can chat. And my availability to the students, I find this was a very good routine. Whereas now the situation has changed. The people, they are not devoting much time, and they are self-centered. I think that attitude has changed. At least I have seen in Qaeda-e-Azam University. In my days, my students, they will work throughout the night if they want to do experiments. Because at the night, everything calm and quiet, they can do experiment quietly. But now, laboratories, they close at 3 o'clock, 4 o'clock. No one is interested. And one thing more which I have noticed in our society, in our Muslim society also, people, they don't want to work experimental physics. Because it's very tough, very difficult. You have to give a lot of time. They feel comfortable to do theoretical physics because they can sit on the computer, they can do anything. I think that attitude is not very good. Look at the development of science. Einstein. Look at the Hertz. I mean, these people who have done the work, basic work, and that is all based on observation, experiments. And theory came later. Like Balmer, he is the man, father of spectroscopy, we call it. He detected this Balmer series. But it was experiment. He observed these lines from the sun spectrum and the sun. And theory came later. And that means theory and experiment, they are side by side. But I think experiment is always more rewarding. I used to teach my students that if you do an experiment and you repeat the experiment after 1,000 years, you will get the same results. Whereas the theoretical interpretation will keep on changing with our understanding, because our understanding is very, very little. So this is the difference between theory and experiment. But experimental physics is tough, I must say. It needs a lot of devotion, lot of time.
A lot of facilities, a lot of money, a lot of investment.
Of course, yeah.
Professor, how would you define atomic physics for the general public, for example?
Well, atomic physics is, I think, one of the basic thing for doing science. What's the atom? I mean, the idea of atom was introduced by so many scientists, but the real picture came when Rutherford he demonstrated that atom contains protons and neutrons and then electrons. And then after Rutherford, Niels Bohr, he actually gave a very good, very clever idea that in atoms, the nucleus is confined in the middle, whereas electrons, they are revolving around it. But there was a basic contradiction in his idea that if the electron is charged particle, is moving in a circle, it must radiate energy. So if it radiates energy, it should collapse with the nucleus. As a result, atom cannot remain stable. And he said, just assume that if an electron revolves in circle orbit, its angular momentum is quantized. People thought, okay, we can make an assumption that it's quantized. Because he can give the explanation, he can calculate the Balmer series very accurately from his formula. And he said, the emission of radiation is only possible when an electron makes a transition from high energy levels to a lower energy level, or it can absorb a radiation from lower level up to the higher level. And these two energies, they are perfect in order. Emission and absorption, they will be exactly the same. H nu is equal to E2 minus E1. And then no one was able to justify it because Maxwell equations, they have given this idea that if charged particle is accelerated, it must radiate energy. Then came de Broglie in 1925. He said that every moving object has an associated wavelength with it. And he gave the explanation that if the electron is revolving in circular orbit, then its 2 pi r, its circumference should be n lambda. That means the wavelength associated with the moving of the electron, it will be the integral multiple, and that must be equal to the circumference of that radius of the circle. So 2 pi r is equal to n lambda, and from there he was able to give a picture that lambda is equal to h over mv. And he recalculated, he proved the condition of Rutherford Bohr that 2 pi r is equal to n lambda is correct, or mvi is equal to nh cross. And on that basis, he was given the Nobel Prize in a very young age. So that was the beginning of atomic physics. And what I have done in atomic physics, that the structure of atom is now very well established. You can make laser of any atom, provided there is some basic requirements. But at the same time, the lasers can be used to probe atomic structure. So this was my research, that I was using synchrotron radiation as well as lasers to probe the atomic structures. And one of the important thing is that when you impinge a laser with the variable energy, as I said, E2 minus E1 should be h nu. So if h nu is the energy of laser, you can keep on changing the energy, so you keep on promoting the electron from lower orbit to higher orbit. At one stage, the electron goes away from the binding energy of the nucleus, and that energy is known as the ionization potential or ionization energy. So my interest in the beginning was to determine this ionization potential value accurately. And there are a lot of groups working in this one. So when I started this research with synchrotron radiation, I managed to calculate the ionization potential of 5 atoms very accurately. And these 5 atoms, these values, they are tabulated by NBS, National Bureau of Standards in America, because they keep a record of the most accurate values determined. So I have this honor that at least 5 atoms, the ionized energy have been made by myself, by my group. So that was my research. Then we thought, what happens if you give enough energy to an atom? Can you promote 2 electrons? It's not an easy thing to do. But if your intensity is high, you can simultaneously promote 2 electrons. And that work we did on helium. And that was only possible with the synchrotron radiation. Otherwise, it was not an easy job. And then I think there was a lot of other work we did on lasers, on the ionizing potentials, and to find out the isotopic shifts as well.
What are Rydberg atoms?
Okay. As I said earlier, a Rydberg atom is a term which is coined by researchers, that if you promote the electron from the lower level up to upper level and you keep on increasing the n value, it will just like a ladder. When n is greater than 30, roughly. Then we call atom as a Rydberg atom. Because its binding with the nucleus loses, and atom become very fluffy, flexible. And these atoms, they are very useful because you have a power to actually pinpoint where the electron goes. Like, I was in America in 1993 on a sabbatical, Fulbright fellow. And there I worked on Rydberg atoms. And I thought, why not to pinpoint Rydberg atom, first promote it to n is equal to 100 or 50, and then it must be moving in the circle somewhere, probability, and then you shoot a laser on it. You never know at what time this laser pulse and the electron, they will be directly in contact. I was not succeeded in that experiment. But idea was that you might be able to see where the electrons most probably is there. But now people have really done a very similar experiments. And they can pinpoint where the electron is. So Rydberg atoms, they have a lot of applications because they are being used as a detector. You know, the N is equal to 103 and 102 in hydrogen atom. That transition is used as a reference in our solar systems. So they detect that one. And the other thing is that the red shift and the blue shifts, I think they are also they are detected only with the lasers. And recently, Chinese, they have managed to send a laser on the surface of the moon, and they have determined the distance between the moon and the Earth very, very precisely. So this is only due to the laser, not a Rydberg atom, but a laser.
Very interesting. How does synchrotron radiation differ from laser technique in probing atom structure?
As I said, synchrotron radiation, it is the radiation emitted by an electron when it is rotated in a circular orbit, approaching the velocity of light, 99.999% velocity of light. When this electron moves from within orbit, it emits the radiation perpendicular to that one when it's in the magnetic field. So that radiation is very, very intense. And its intensity is mainly concentrated in the ultraviolet region, X-ray region. X-ray is 0.1 nanometer, and that is the size of the atom also. So you can actually probe the atoms beautifully with the X-ray radiation. And that is not a monochromatic radiation. It contains all the radiation from the gamma rays up to visible. So you can do the absorption experiments beautifully, because you don't have to sort of tune it. So, you have a continuous light source. Like sun, it emits a radiation, and we can use sun radiation as an absorption, as a light source to do the absorption spectroscopy. But the only difference is sun has a lot of, one can say, missing radiation that gets absorbed by the air. So it's not a continuum radiation. It has some structure into it. Whereas synchrotron radiation is a structureless. It's a continuous radiation. So you can do experiments beautifully on that one. You know, you put your sample, you send emission, the radiation from a synchrotron, and the other side you can record the transmitted light, like Lambius-Beard law. So that gives you the absorption coefficients very, very accurately. You cannot do these experiments with any other light source. So that's why in the world, synchrotron radiation are very, very popular, but the machine is very expensive. I will tell you about Sesame later. So this was my first experience to do plain absorption spectroscopy with synchrotron radiation. Then you asked me about lasers. So lasers, these are the radiations because they are monochromatic. They emit only one wavelength radiation, like they can emit blue or red or yellow. So you can only use that radiation as a probe, but you cannot do absorption experiments. For that, you need to have another source known as dye laser. So you can use laser to pump a dye. So this dye will emit a radiation of a continuous radiation of a band maybe 100 or 200 nanometers, and that can be used exactly like we are using synchrotron radiation. So I have this experience of working on both these light sources. So this is the basic difference. The synchrotron radiation is a continuous radiation continuum, whereas lasers, they are discrete, monochromatic. But now people have developed a very good facility. They have put some undulators or insertion devices in synchrotron to make this radiation as a monochromatic. Or you can put some monochromatic there. You can also make it monochromatic. But the main idea is that synchrotron is a continuum radiation.
Very interesting. Professor, which research result or experiment do you personally consider a turning point in your career, in your journey?
I think all the work I have been doing or I have done, I think I like it very much. But I was very much excited when I managed to do an experiment here in Pakistan with the helium atom. You know, anything you do about hydrogen atom, because it's one electron system, you can do a theoretical model excellently, there's no issue. You can publish it very easily. And anything you do on helium, that is again a very important, a two electron system. So you have to introduce some approximations. But if you do an experiment, then the theoretician, they have to think about it. What possibilities are there to explain the observed structure? When I came here, I developed this laser laboratory. And you know, the helium, to excite from the ground state to the first exciter state, you need about 19 electron volt energy. It's a very high energy. So I thought about it, how I can excite the helium atom from the ground state to the first metastable state. And the idea was to generate a discharge. If you have a discharge, helium atom, they will go to the metastable state. And then their lifetime is about milliseconds. And then I can use another laser. And I can promote the atom from that metastable up to the upper levels. And that was my first experiment. I was so excited when I managed to study the helium atom from the metastable state up to the ionization limit. And I published the paper in Physics Review because I was so excited. Then one of my professors in Germany, he wrote to me. He said, "You are doing an excellent work. Why don't you measure the photoionization cross-section at the ionization threshold? And you can also do the measurement of cross-sections from different exciter states." So I liked this idea very much. Then I involved 2 students to measure the photoionizing cross-section from different exciter states up to the ionization threshold. And then there was theoretical work that you should extend the cross-section above the threshold. So then it was a new opening for us. And we did a lot of work, and our work was cited quite a lot by the people that this is really a very good work. And recently I was invited to write a review article on the measurement of photoionizing cross-section based on my contribution in this field. So that was published about a couple of years ago. And I was really very happy that at least I have contributed to what I have done and compiled for the generation to come.
MashaAllah, MashaAllah. Congratulations, Professor.
Thank you. Thank you.
Professor, what are the main challenges in laser isotope separation of light element like lithium?
Well, we can make an atom bomb by enrich the uranium 235, 238. We can separate that one. But lithium is now being replaced. Uranium is being replaced by lithium. When I built this equipment for time of flight mass spectrometer, the first thing I did let's work on lithium. Lithium has two isotopes, lithium-6 and lithium-7. Lithium-7 is very common, whereas lithium-6 is very rare. But you can enrich it. Laser is a perfect source to enrich any isotope. The reason is every atom is neutral. When you excite it, even it remains still in the excited state but neutral. But if you ionize it, that means now it has charge. Once it is charged, you can apply electric field just to accelerate it or magnetic field just to rotate it. So this was the idea behind isotope separation, that you take a laser, but laser has to be high power and it should not excite the atoms of lithium-7, only lithium-6, or you can only excite lithium-6 or lithium-7 so that you can separate these two atoms. Once lithium-6 is excited, then you can use another laser to ionize it. Now, once it ionizes, now you can apply a magnetic field. You can separate lithium-6 and lithium-7. This is the basic idea of isotope separation. But the requirement is, here one photon can ionize only one electron. So you have to have a very high intensity laser, number of photons falling per unit area, per unit time. That should match the number density of the atomic beam that you are making. So when I did this experiment, first I made the atomic beam apparatus so that I can control the number density, about 10 to the power 12, 13. Then I built a laser of that wavelength just to excite it. And that was also comparable to the number of atoms in the beam, so that I can ionize each and every atom. It is 100% kind of purity. Only in one single goal you can separate the two isotopes very precisely. But the only thing is, the yield is very little because you have to work very hard. If you work the entire day, maybe you can get 1 milligram or 2 milligram. And that is not sufficient to make any useful thing. But when I did this experiment, I proposed another way of ionization. And that was 60% efficient, more efficient than people are using. And I published this paper. And I got a lot of requests from different people that how did you manage that? Although I explained each and everything, but they wanted to know more. I went to Jordan. In those days, I was working as a director of science in Sesame project. And Professor Khalid Toukan, he was the director. I gave him my paper. He was so excited about it. He said, this is an excellent work you have done. And you had told the people, what is the way to separate isotopes? And then, having done that separation, then we demonstrated what is the percentage of lithium-6 and 7. And for that, we built this time of flight mass spectrometer. And once I did that one, I was given the award by the government of Pakistan. It's known as Hilal Imtiaz. So before that, when I built the atomic beam apparatus, I was given the prize Stara Imtiaz. And before that, when I started this laboratory, I was given the Tamgamda. So I have no regrets coming back from Germany and establishing a laboratory in Pakistan and contributing positively. I think no regrets. The government has really honored me a lot.
MashaAllah. You deserve it, MashaAllah.
Thank you.
Professor, where do you see its most promising future application? I mean, laser in general, and especially the isotope separation of light element like lithium.
The future is very, very important, particularly if you are using isotopes. You can make atom bomb. Of course, you cannot use laser isotope separation. You can use it, but it's, as I told you, the yield has to be enhanced. We have this facility in Pakistan. Russia has a very huge facility. But we stopped funding this project because its yield was very low. And therefore, we moved towards the other option, like Qadir Khan has opted the rotator, where you can separate yield is very high. But the application of the work I have been doing is very important. You know, the rare earths. Rare earths are very important, and we in Pakistan we have got a lot of deposits of these rare earths. And I started this work here in Pakistan just to identify where are the deposits of rare earths, and then what are their compositions, and how much is sort of rare earths there. And I took one PhD student, and we worked very hard. We managed to give the locations, and we published this paper in America. Then I sent my student to America, where he got more training. And we have, last month, we have published paper on the rares. The idea was just to help my country to explore our resources. Where are the rares, and how to explore them, how to extract them. So this is my future activities, and I'm working on it, and how to do that one.
MashaAllah. Professor, what were the biggest practical challenges in building your laboratories at Quaid-e-Azam University in 1986?
Well, you know, when I came back from Pakistan, I was given a laboratory. It was empty, just a room. And then I had to move around to find some funding source so that I can buy some equipment. And I was lucky that in those days, Dr. Ashfaq Ahmad, he was the chairman PAC, and I talked to him. He gave some money. I got some money from Qadir Khan and from UGC. And that was, but I have to work very hard to convince these people. It was not easy. At the same time, I talked to Abdul Salam Sahab that how can he help me. He introduced me to another fellow from ICTP Trieste, Professor Dinardo, and he asked me to write a proposal. And I wrote a proposal. He gave some funding and some equipment. And in the beginning, I really worked very hard to establish this laboratory. But once the laboratory was in shape, then I got a lot of support from different corners. And in particular, when UGC was reformulated into Higher Education Commission, and Dr. Atar Rahman, he became the chairman of HEC. He had a brilliant idea that he will support PhD students with certain amount. And then he also gave an option that if you have 4 students or 5 students, you can combine this money. So you can buy a big equipment. So I was lucky in those days. I had 5 students who are funded by HEC. I combined their amount and I purchased a lasers. And that has given me a boost because without laboratory, without equipment, you cannot do anything. I think this was a very tough time in those days. And through this support from different corners, I managed to establish a laboratory. And then this laboratory is now internationally very well recognized. People, they report Baig's group in Pakistan. I think that is a great honor if somebody writes that his group is doing this one. And based on our experimental measurements on the photon cross sections, one Chinese, he developed a theoretical model. And when I got this paper, I was feeling so happy that he was using our measurement to develop his theoretical model. So to develop a laboratory is not an easy thing. I think you have to really devote a lot of time. I used to go to Germany almost every year for 2 months because this was in contract with the German co-partners. And when I come back to Pakistan, my luggage was full of equipment only. And my wife says, why are you purchasing these things? Why don't you purchase some gifts for us? So I used to tell her, look, I have to develop a laboratory for my nation. So this is the way how I really managed to build this laboratory. And I think it's one of the best laboratory, even now, very well equipped. You name anything, you'll find it there.
Inshallah. Professor, what is the ideal balance between fundamental and applied research that Pakistan Academy of Sciences aims to achieve?
Well, in my opinion, there is no difference between applied and basic sciences. The basic science for today will become applied science tomorrow. So everything is applied. I think it's a wrong bifurcation. We should support basic as well as applied, both. We have not made any bifurcation that we will not support basic science. We are supporting basic as well as applied, and this is my idea. You should never ever try to do that. Although people, they say applied, but I think applied, you need basic understanding first. As I told you, I started basic sciences, but then I converted myself to applied sciences. I'm building equipment now. It is all based on my basic sciences. So this is not a good idea to sort of say basic and applied sciences. Maybe in the internationally they are saying 40 to 60%. 60% applied and 40% basic sciences. But I think 50-50 is fine. There's no hard and fast rule.
But
we should support both, basic as well as applied sciences.
But sometimes there are a huge difference between applied and fundamental science, like, of course, Higgs boson. It's predicted on 1964 and it's applied.
Yes, look, theory is not costing you much money, one thing. You have to sit down, you can work at home. When Higgs proposed way back in 1960 Higgs boson, he was not expecting anyone will do the experiment. It's only very recent, 2012, that Higgs boson was discovered, and they have completed the, one can say, it is the model which is sort of explaining all the fundamental constituents. But this standard model, I think people are working beyond standard model. So there is no end to that one. Whereas experiment was limited. To do this Higgs boson, discover Higgs boson, you need a very, very high energy accelerator. And that is only possible while doing experiment at CERN. That's why it took so long. As I said, of course, experimental physics is expensive, but we have to keep on funding experimental sciences. Look, there is another experiment going on, ITER, in France. ITER, I call it ITER of eat everything. And we have put in so much funding in it. And up to now, no outcome yet. I think Chinese are doing a great job. They have already demonstrated the artificial sun. But ITER now, first they said it will be ready by 2015, then in 20, And now they are given the time 2035. I don't know.
Professor, how do you see the relationship between fundamental research like yours and the constant needs of society and the economy?
Look, fundamental science, applied sciences, and society, I think they are interrelated. You must always think in terms of contribution towards your society. If you do fundamental sciences, basic sciences, I think still you are helping your people in the society. Once you do an experiment, you develop something, and that is again for society. I think science for society, not society for science. I think science has to deliver to deliver to the society. And I have always that in mind, that whatever you do, think your society first. Ecology, what is that? I mean, you think about where you are living, what are the issues around you, and you try to do research on that issues, not the issue which are not our issues. So that is important. Think about the society and look there for the issues and try to give some solutions. And that is the way science can really help our society. And we should always do that one.
Science for society.
Yes.
Not society for science.
Exactly.
Thank you very much.
It's really pleasure to be here, Mustafa. And I feel so honored that you invited me. And I have spoken very frankly.
Thank you.
As frank as a friend. And we had tried to touch upon different issues, how we should tackle these issues and do something betterment for our community.
So, thank you very much.
Thank you.
We need another episode with you.
No issue. I'm available.